Welcome to Section 3, Lesson 9. Across the previous 8 lessons, we built every solving technique for linear equations and inequalities, including absolute value variance and compound forms. Across Section 2, we built the words to Algebra Translation Toolkit, Keyword Dictionary, Trap Library expression templates. Today, we put both halves together and solve linear word problems end to end. Word problems are the natural completion of the entire Section 3 project and the form of problem you will see most often on standardized tests, in introductory science courses, and in real-world applied work. The lesson is mostly about disciplined workflow rather than any new algebra. The 4-step framework define, translate, solve, verify is the universal recipe for every word problem in the rest of the algebra course and well beyond. First idea on the board. A word problem is an English description of a situation that asks for a specific numerical answer. The path from the English description to the answer goes through 3 intermediate stages: a variable definition that names the unknown, an algebraic equation or inequality that captures the relationships described in the English, and a solution to that equation that produces the answer. Skipping any of the 3 stages, especially the variable definition, is the most common reason students get stuck on word problems. The discipline to walk through all 3 stages on every problem is the single biggest unlock for word problem fluency. Second idea, the 4-step framework is step 1, define the variable. Step 2, translate the English into algebra. Step 3, solve the equation using Section 3 techniques. Step 4, verify the solution by substituting back into the original English context. Each step has its own moves and its own common errors, and treating the 4 steps as separate, distinct phases prevents most of the confusion that blurry workflows cause. Today we walk through 2 clean examples covering 2 different problem templates with the 4-step framework explicit on every step. The verification step in step 4 is even more important on word problems than on plain equation problems, because the algebra to English translation can be wrong even when the algebra to algebra solving is perfect. The verification consists of plugging the numerical answer back into the original English description and checking that the described situation makes sense and is internally consistent. Sarah is 12 and Bob is 24, Sam is 36, Sarah is half of Bob, all consistent with the original sentence. The verification catches translation errors that pure algebra checks would miss and is the cheapest insurance you can buy on every word problem you ever solve. Word problems convert from an English description to a specific numerical answer through 3 intermediate stages: a variable definition, an algebraic equation, and a solution to that equation. Skipping any stage, especially the variable definition, is the single biggest reason students get stuck. The 4-step framework treats each stage as a distinct phase with its own moves and prevents the workflow blur that causes most word problem confusion. Step 1 is define the variable. Read the problem and identify the unknown that the question is asking for. Write a 1-line variable definition assigning a letter to that unknown. If multiple unknowns exist and they relate to one another, assign the simplest one a letter and express the others in terms of it. The variable definition is the foundation of everything that follows. Without it, the algebra has nothing to refer to. Step 2 is translate the English into algebra. Use the keyword dictionary from Section 2, Lesson 5, and the trap library from Lesson 6. Identify the relationships described in the English and write them as one or more algebraic equations involving the variables. Combining the relationships often produces a single equation in the single defined variable, ready for solving. Step 3 is solve the equation using Section 3 techniques. The equation produced by translation is typically a 1-step or 2-step linear equation, sometimes with variables on both sides or with parentheses to distribute. Apply the inverse operation procedure with reverse PMDS order to isolate the variable. The solving phase is mechanical once the translation is done correctly. Step 4 is verify the solution in the original English context. Substitute the numerical answer back into the variable definitions and check that the described situation is internally consistent and matches the original problem. The verification catches translation errors that the algebra checks would miss and is much faster than re-deriving the entire solve. Always include the verification step as a non-negotiable final move on every word problem. Here is the first worked example. The problem: Bob is twice as old as Alice, and the sum of their ages is 36. How old is each? The unknowns are Alice's age and Bob's age, and the relationships connect them through a multiplier and through their sum. Apply the 4-step framework explicitly. Step 1. Define the variable let A equal Alice's age in years. Then Bob's age is described as twice Alice's age, so Bob's age is 2A. Both unknowns are now expressed in terms of the single variable A, ready for translation. Step 2. Translate the English. The phrase the sum of their ages is 36 becomes the equation A plus 2A equals 36. Combine like terms on the left to get 3A equals 36. The translated equation is one variable linear, ready for the lesson 1 solve. Step 3. Solve the equation. Divide both sides of 3A equals 36 by 3. The result is A equals 12, so Alice is 12 years old. Bob's age is 2 times Alice's age, so Bob is 2 times 12 equals 24 years old. Step 4. Verify in the English context. Bob is 24, Alice is 12, 24 is twice 12, sum is 24 plus 12 equals 36. Both relationships hold and the situation is internally consistent. Translation and solving verified. So Alice is 12 and Bob is 24. The big lesson from this example is the 4-step framework applied cleanly to a classic age problem. The variable definition assigned the simpler unknown to a single letter and expressed the related unknown in terms of it. The translation step produced a one-variable linear equation. The solving step was a clean one-step divide. The verification confirmed both the multiplier relationship and the sum relationship. Every age problem you encounter for the rest of the algebra course follows essentially this exact rhythm, and building the rhythm now through deliberate practice on a few dozen problems is the most efficient use of your study time at this stage of the curriculum. Here is the second worked example. The problem: 2 trains leave the same station traveling in opposite directions. Train A travels at 50 miles per hour and train B at 70 miles per hour. After how many hours are they 360 miles apart? The template is distance, rate, time, with the twist that the 2 trains contribute to the separation simultaneously. Step 1. Define the variable. Let t equal the number of hours since both trains left the station. The distances each train has traveled depend on t through the distance, rate, time. Template: train A has gone 50 t miles and train B has gone 70 t miles. Both distances are now expressed in terms of the single variable t. Step 2. Translate the English. Because the trains travel in opposite directions, the total separation between them is the sum of the 2 individual distances. 360 miles equals 50t plus 70t. Combine like terms on the right to get 360 equals 120t. The translated equation is one variable linear. Step 3. Solve the equation. Divide both sides of 360 equals 120t by 120. The result is t equals 3. So the trains are 360 miles apart after 3 hours of travel. Step 4. Verify in the English context. After 3 hours, train A has traveled 50 times 3 equals 150 miles in one direction, and train B has traveled 70 times 3 equals 210 miles in the opposite direction. The total separation is 150 plus 210 equals 360 miles, which matches the original problem statement exactly. Translation and solving verified. So the trains are 360 miles apart after 3 hours. The big lesson from this example is the distance, rate, time template applied to a two-mover scenario. The key insight is that opposite direction motion adds the two distances to give the total separation, while same direction motion subtracts them. Recognizing the geometry of the motion before writing the algebraic relationship is the only conceptually distinctive piece of distance, rate, time word problems, and after a dozen or so practice problems, the pattern recognition becomes automatic. The rest of the workflow is the standard four-step framework you used in the previous example. 3 mistakes that catch every algebra student during their first weeks of word problem work. Each one is fixable with a small explicit habit applied on every problem. First mistake, skipping the variable definition step and jumping straight to algebra. A student reads a problem and immediately writes an equation involving x, without ever writing down what x represents in the problem context. Halfway through the solve, the student loses track of which unknown x is, mixes it up with a related quantity, and produces a wrong answer, or worse, the right number for the wrong question. The fix is to always write a one-line let statement at the top of the work, let x equal the specific quantity with units. The variable definition takes 10 seconds and prevents an entire class of late-stage confusion. Second mistake, recognizing the wrong template for the problem and applying inappropriate algebra. A student sees a percent problem like a salary increased by 10% now equals 55,000 and tries to set up a linear template equation like 55,000 equals salary plus 10,000, which uses the wrong template entirely. The correct template is the percent change template from section 2 lesson 7, 55,000 equals salary times 1.10. The fix is to deliberately scan for keyword markers like percent, ratio doubled, increased by, distance equals rate times time before writing any algebra, and to consult the section 2 template library when the right template is not immediately obvious. Third mistake, verifying the algebra correctly but never checking the answer against the original English description. A student solves an equation and gets x equals 12, double checks the algebra arithmetic, and submits 12 as the final answer without ever rereading the original problem. If the translation step had a sign error or a unit confusion, the algebraic answer is correct for the wrong problem, and the verification step would have caught the issue. The fix is to always reread the original problem after solving and confirm the proposed answer satisfies the original described situation. Linear word problems are the dominant form of math problem on standardized tests, in introductory science courses, in business case studies, and in real-world applied work. The four-step framework you learned today is essentially universal across all of these contexts. 4 broad sectors below. On the S08 ACT GRE and most state algebra exams, the math sections are 60 to 70% word problems requiring the 4-step framework on every problem. Test writers know that students who have practiced the framework move through these problems in under a minute each, while students who have not practiced struggle and lose points to time pressure. Drilling word problems with the explicit 4-step framework is the single highest leverage test prep move you can make for any of these exams. In contest math, the AMC, AI math counts, and similar problem sets use the 4-step framework on every problem, often with 3 or 4 templates layered into a single problem statement. Contest math students train mixed word problem practice intensively for exactly this reason. The skills you are building this week scale directly into contest math fluency for students who choose to pursue it. In physics homework, every kinematics, dynamics, and thermodynamics problem is a word problem at heart, requiring the same translate, solve, verify rhythm with physics-specific templates replacing the generic algebra templates. The 4-step framework is exactly the same, only the specific templates change to formulas like distance, rate, time, force, mass, acceleration, work, energy. Physics students who have internalized the framework move through homework noticeably faster than those who solve each problem from scratch. In business case studies and entrepreneurship coursework, pricing decisions, capacity planning, and break-even analysis are all word problems requiring the four-step framework with finance-specific templates. Decision support, forecasting, and operations research at the professional level all rely on the same disciplined translate, solve, verify rhythm, scaled up to many variables and many constraints. The skills you build today are the everyday currency of applied analytical work across the entire economy. 3 things to take with you from this lesson today. Linear word problems are the highest leverage practical application of the entire algebra course up through section 3. And the 4-step framework you build today scales directly into every later word problem chapter and into the introductory chapters of every science and engineering course you take after algebra. First, the 4-step framework define, translate, solve, verify is the universal recipe for every linear word problem in the rest of the algebra course. Each step has its own moves and its own common errors, and treating them as 4 distinct phases prevents the workflow blur that causes most word problem confusion. Practice the 4-step rhythm explicitly on a few dozen problems, and the framework becomes automatic, freeing your attention to focus on the harder template, recognition, and translation craft moves. Second, the variable definition step is non-negotiable on every word problem. Always write a one-line let statement at the top of your work assigning a specific letter to a specific quantity in the problem, with units when applicable. The variable definition is the foundation that every later step refers to, and skipping it is the single biggest reason students get lost mid-solve on word problems. 10 seconds of deliberate variable definition prevents minutes of late-stage confusion. Third, always verify the proposed answer against the original English description, not just against the intermediate algebra. The verification catches translation errors that pure algebra checks would miss, and it costs only 15 to 30 seconds per problem. Read the original problem one more time after computing the answer and confirm the described situation is internally consistent with the proposed numerical solution. The English context verification habit is by far the cheapest insurance you can buy on every word problem you ever solve, and it pays off again and again across every test, every homework set, and every applied problem you will encounter for the rest of your math career. Build the habit deliberately on every problem this week, even when you feel certain the algebra is right, and within a few weeks the verification step becomes automatic and uses almost no conscious attention. Coming up next, the lesson called Section 3 Marathon, where every solving technique from Section 3 is applied back-to-back on a mixed sequence of equation, inequality, absolute value, and word problem challenges. The marathon is the natural completion of Section 3 and the practice format that builds the speed and pattern recognition needed for tests, contests, and the linear modeling work of Section 4.